Exercise 12.1 is really a review of the Alkene addition reactions. So I would encourage you to go back to that recipe list, try to memorize those learn those by heart, and then approach this problem. There's just one exercise here that's new. That's turning an alkane into a haloalkane. How do you add a halogen onto a hydrocarbon? If you ever have an alkane, there are only two reactions you can do with it. You can light it on fire and turn it into carbon dioxide and get some energy out of it, or you can do a radical reaction. So if we see that bromine adds, we would add molecular bromine, or we could use NBS if we wanted to. So we could also do NBS, N-bromosuccinimide. And then we have to have light, and that's H nu. So H in this V-looking thing is the Greek letter nu. It stands for the frequency of the light, how frequently the light waves are hitting you. And that corresponds to the energy of the light. So if you do this radical reaction, it puts a bromine on the most substituted carbon of the alkane. And that opens up the world to you, because once you have a bromine or a halogen on a hydrocarbon, it can act as a leaving group. And that means you can do substitution reactions, elimination reactions. And once you do elimination reactions, as we'll see, you can do all of the addition reactions. So that's that first step. If you ever have an alkane, that is a real help, because it means you have to do a radical reaction. It's your only choice. Or you could light it on fire and turn it into carbon dioxide and energy. Okay, so let's think about this next step. Now, once you have an alkane, a haloalkane, once you have a halogen on there, that's profoundly significant, because now you can do an elimination reaction, and you want to see elimination reactions from two perspectives. In the one hand, the forward perspective is you eliminate the halogen, so it's not there anymore. The reverse, another perspective is you create a pi bond. Every time you do an elimination reaction, you create a pi bond. So here, we can create this pi bond. Now, notice that the halogen, the atom the halogen is on is the alpha carbon. Each carbon next to that is a beta carbon. Notice that there's symmetry in this molecule, so these two beta carbons are really symmetrical. So I'm just going to consider one of them, and actually, I'll just consider one of them. Now notice you could make the pi bond in two directions. It could either be going down, that's how we want it, or it could be going up. Those are two different elimination products. So let me draw the product. If it had gone up to the other beta carbon, this is the alkene that we would have had. Let me actually. That's the alkene we would have had. Now we don't want this one. So if we have to choose between these two alkenes, you want to think about which one is more or less substituted, and whether you would use a bulky base or a skinny base to accomplish that. So if you're looking at this first one, the one that we don't want, and we think about how many carbons are coming off of carbons in the double bond, we have 1, 2. That is di-substituted. The one that we want has 1, 2, 3 carbon chains coming off of the carbons in the double bond, and so that is tri-substituted. So we want the more substituted one, the tri-substituted one. If you remember, that's the Zaitsev product, and to get the Zaitsev product, you always add a skinny base. So examples of skinny bases are sodium hydroxide, or sodium methoxide, or sodium ethoxide. All of those are skinny bases that would give you that Zaitsev product. And that illustrates why, having a halogen on this molecule is so exciting. Because once you have a halogen, you can do this elimination reaction, and when you do an elimination reaction, all of the addition reactions are available to you. So let's think about all of these many, many addition reactions one by one. First, up here to the top left, what we're doing is adding a bromine. We could see that pretty clearly. We're adding a bromine, and also it doesn't look like we're adding anything else. Now we definitely are. There's no hydrogen here, and there is an implied hydrogen on this atom. So really we're adding an H and a Br. Okay, so far it looks like hydrohalogenation. But remember, HBr all by itself would add Markovnikov. The hydrogen would go to the less substituted carbon, and the bromine would go to the more substituted carbon. Here, the bromine, this carbon that the bromine is on, is bonded to two other carbons, so it is secondary. And the carbon the hydrogen is on is bonded to three other carbons, so it is tertiary. The hydrogen went to the more substituted carbon. That is anti-Markovnikov addition. And so you'd want to add peroxides, ROOR, in order to get that anti-Markovnikov addition of H and Br. Okay, then let's look at the next possibility. Similar thing. So here again, we're adding the bromine onto that one carbon, and we're also adding a hydrogen here. This has only one hydrogen on it. Oops. This has only one hydrogen on it, and this one has two. So you can see that you've added a hydrogen. So adding an H and a Br, that would be hydrohalogenation, HBr. Notice that this carbon at the top is bonded to 1, 2, 3 carbons, so it is tertiary. The carbon at the bottom is bonded to 1, 2 carbons, so it is secondary. Notice that the hydrogen went to the less substituted carbon. That's Markovnikov addition, and so you don't add peroxides here. You just leave it as HBr. You get Markovnikov addition of H and Br. Okay. This next one is really useful because it's a way to do something kind of unique, and that is to break a carbon-to-carbon bond. So we'll see the significance of that as these exercises progress, but in this next one, we're trying to break a carbon-to-carbon bond. After all, we have a ring here, and in our product, we don't. Not only that, but we have double bonds to oxygen. Now, we've only learned one reaction to do that. One reaction that will create double bonds to oxygens. That's ozonolysis. So we can use ozone here to break this bond and replace it with double bonds to oxygens. Ozonolysis. Well, the recipe for ozonolysis is slightly different for an alkene and an alkyne. So you'd want to make sure that you notice that that is an alkene. And so our recipe here will first be ozone, and second, DMS, dimethyl sulfide. And what that does is, here, let me just get this molecule here. So what that'll do is it will break the double bond between the carbons. And where that bond was, so you break that double bond, and where it was, you would add carbonyls, double bonds to oxygen. Now that doesn't really look like this just yet, but remember that whenever you form these ozonolysis products, number the chain and redraw it in a more conventional way, because it's almost always the way that it would be shown on a standardized test. So here, if we count here, it's 1, 2, 3, 4, 5, 6, 7. Now I'm numbering these not to name it, so I'm not being rigorous about the way I'm numbering it. I'm just numbering it to keep track of stuff. I'm going to number this one also, 3, 4, 5, 6, 7. And what you'll notice is that we have a carbonyl on carbon 2 and on 7, and that we have 7 carbons. And so you can see, once you number this, that these are really the same molecule. Okay, let's try this next one. What we're doing is we start with an alkene, and we're adding 2 OHs, 2 hydroxyl groups, cis. Now we're getting this arrangement and also the enantiomer. The enantiomer would be if both of the OHs were going away and this methyl group were coming out at us. Well, there are two ways you could do this. You could use osmium tetroxide, and that would give you one possibility. You'd want to follow that up with sodium bisulfite. You could also use potassium permanganate at a cold temperature, so something like 0 degrees Celsius, but cold, and also you'd want some sodium hydroxide in there. So that's the syn dihydroxylation that we would have learned in that alkene chapter. Now, if you want to add two hydroxyl groups trans to each other, then you would use a peroxy acid. Now, you could just use any peroxy acid. Remember, that would be RCO3H. And the structure for that, if you remember, is kind of like a carboxylic acid. So a carboxylic acid is carbon double bonded to oxygen with an OH, but it's peroxy, so you have a lot of oxygen, so you insert another oxygen in there. So that's your COOH, your CO3H, your peroxy acid, and then you follow that up with a water or an acid wash, so H3O plus hydronium. Keep in mind, one very common peroxy acid is MCPBA. That one will come back in organic chemistry too. And remember that what this does is it turns an alkene first into an epoxide. So after the first step, your alkene would look like this, that three-membered ring with an oxygen there. And I think there's an exercise later on in this packet that uses this MCPBA just to create the epoxide, and then this H3O plus opens that epoxide ring and gives you your two hydroxides anti to each other. So that's anti-addition or AntiDihydroxylation, anti-addition of two OHs. For the next one, we start with an alkene, and we see that we add an OH and a Br. That's halohydrin formation. Notice also the OH goes on the more substituted carbon, and we get both enantiomers, a racemic mixture of those. The recipe for that was Br2 and then H2O. The alkene attacks the Br2. One of the bromines adds in a sort of ring called a bromonium ion. The other bromine acts as a leaving group, and then water comes in as a nucleophile and attacks the more substituted position, because that's the position the bromine is leaning away from, because it can handle a slight positive charge, and then you just do a proton transfer to turn the H2O into an OH. So, hydrohalogenation. Going below, we see that we add two bromines anti to each other. That's bromination. So just Br2. One bromine adds and forms that bromonium ion, and then the other bromine comes in as a nucleophile to attack from the opposite side. So it's anti-addition. Here, it looks like we just erased the pi bond, but actually we add a couple things. It's just what we add is implied. Notice there's no hydrogens here, there's only one hydrogen here. In this molecule, there's one hydrogen there, and there are two hydrogens here. What we've done is we've added two hydrogens. This is a hydrogenation. And with alkenes, hydrogenation is just H2, so you bubble hydrogen gas through, and you treat it either with platinum, palladium, or nickel. Not all three, just one of those catalysts, and that will turn your alkene into an alkane. Now here, what we're doing is we are adding an OH. That should be clear enough. But what we're also adding is an H. If you notice, again, there's no hydrogen on this carbon, but there is a hydrogen here. And if you draw it in, notice that this carbon is tetrahedral, so it should have two bonds in the plane, one coming out and one going away. If you draw the hydrogen in, you see that it added on the same side as the OH. This is syn hydroxylation. So these H and OHs, or synhydration, I should say, because you have an H and an OH adding. H and OH, that's like H2O, so it's like adding water onto the molecule. Notice also that the H goes onto the more substituted carbon. So this is anti-Markovnikov addition. There's only one way that you know to make anti-Markovnikov addition of H and OH, and that's hydroboration oxidation. So if you ever see the hydrogen add onto the more substituted carbon of an alkene, and the OH add onto the less substituted, then you know you have to do hydroboration oxidation. For alkenes, that recipe was you could either use borane, stabilized by tetrahydrofuran, or you could just use 9-BBN. And the truth is, if you ever go into a laboratory and do this, I would encourage you to use the 9-BBN, because these boron compounds are really toxic, and 9-BBN is a solid, so it's easier to contain, whereas this BH3 is a gas, so it's much harder to contain. So that's the first step. That adds hydrogen and boron. That's the hydroboration. And then you have to replace the boron with an oxidation, with an oxygen. So you do an oxidation. You add hydrogen peroxide, H2O2, and sodium hydroxide. Now notice, we're not spending a lot of time on the mechanisms for these. We spent that time in the we spent time on that in the previous chapter when we introduced these, and I have videos on that. I encourage you to go back and review them. It might help you out a little bit. What we're focusing on in this chapter is thinking about these recipes as a chef, thinking about what changes we can accomplish. How they happen, that is a separate discussion. Okay, last thing here. In this case, we're also adding an OH. That much is clear. What may not immediately be clear is we're adding another H as well. This has only one hydrogen on it. This carbon has two. So really, we're adding an OH and also one of these H's. So it's another hydration. Now this one, in this case, the hydrogen that we added onto the less substituted carbon. That's Markovnikov addition. And we know two ways to do Markovnikov addition of H and OH. Two ways to do Markovnikov hydration. The first one is just acid-catalyzed hydration. You could use water and a strong acid like sulfuric acid, H2SO4, or if you prefer, you could just write H3O+. Because if you put a strong acid into water, whoa, sorry about that. If you put a strong acid into water, the acid gives away all its H pluses, and so the water really just becomes H3O+. So either way, that would accomplish that transformation. The one liability with acid-catalyzed hydration is you form a carbocation intermediate in that reaction, and that carbocation can rearrange. Now here we don't have to worry about carbocation rearrangement. The carbocation would form on this tertiary carbon, and there's nowhere it would rearrange. But just to review, if you didn't want rearrangement, and it could occur, the other way to do Markovnikov hydration, to add an H and an OH, where the H goes on the less substituted carbon, is oxymercuration demercuration. And so that involves adding mercury 2 acetate and water in the first step, and then second, sodium borohydride in the second step. This reaction will come back again in organic chemistry too, so it's worth investing a little time to remember that now. In fact, it'll come back and there'll be another complication with it. So if you can really remember it well now, it'll help you in the future. Your future self will thank you. So what we've seen in this exercise is that we can start with a molecule that's barely reactive at all, do a radical reaction to put a halogen on it. Once you have the halogen on it, you can do an elimination reaction. We saw that here we wanted the Zaitsev product, but you could have just as well gotten the Hoffman product if you wanted. And then crucially, once you have an alkene, the world of addition reactions is open to you. So many possibilities, so many different chemical behaviors that you can create inside of systems, living or non-living, and all because you had a halogen, all connected to a simple hydrocarbon with a radical and an elimination reaction. So hopefully this helps you to see the significance of this radical reaction. You can turn an alkane into almost anything with this, and hopefully this also served as a good review of, or at least an introductory review of the alkene reactions from that previous chapter. In future exercises, we're going to use these in multi-step syntheses. So each of these arrows was just representing a one-step synthesis. We're going to use these in succession in future videos.